Hello students, let's learn how to perform calculations with warming curves. So, we learned how to interpret and the basic setup of a warming curve. And for our purposes in honors, we definitely are just going to be working with a warming curve or cooling curve with water. So definitely trust that. All right, can we tie this in with these terms that we got? And I actually have the values for water. The molar heat of fusion of water is 6 kilojoules per mole. So this is what we have to invest to convert 1 mole of water from solid to liquid, to completely melt it once it's at its melting point, where it would require almost 41 kilojoules to fully vaporize 1 mole of water at its boiling point. It should make sense why these are such different values, even though they're for the same quantity of water. To vaporize, you have to overcome particle attraction, where to melt, you just have to equal the particle attraction. We know this. So we can definitely anticipate molar heats of vaporization to be much larger than molar heats of fusion. And if we know how much substance we have, so let's just say that we have 5 grams of water, and let's say that it is at 0 degrees Celsius. How much would it take if those 5 grams were water solid? How many joules would be required to invest to convert this all to liquid? Well, if we are undergoing a phase change, and solid to liquid would be the molar heat of fusion. Okay, and we definitely are endothermic, so we're investing this. I want to know, how many joules do I have to invest to be able to accomplish this? All right, well, let's start with our mass of water. That is just a mass, where I'm probably going to use this, but this can be written as a conversion factor. I have to invest 6 kilojoules of heat energy for every 1 mole of water. Well, to be able to utilize this relationship, I know I have to convert grams into moles. So, water, 18.02 grams for every 1 mole. And, provided that 1 mole of water requires 6 kilojoules to be invested, so it's positive. The question would be asking for joules, however, and we know that 1 kilojoule would be 1,000 joules. And so, ladies and gentlemen, let me just grab my calculator, and to do this, I'm going to multiply everything in my numerator, 5 times 6.0 times 1,000, and then I only need to divide by my 18.02, and sig figs 2, and so 1,700 joules are what have to be invested to take 5 grams of water. So that would feel like 5 paper clips. That would be about 5 milliliters, a really, small puddle of water in your hand. It takes 1,700 joules. So it takes about 1 joule of energy to change 1 gram of water 1 degree Celsius, remember, or 4. Oh, what am I thinking? Please ignore what I just said. Remember, 1 joule is the amount of energy that has to be invested to lift 1 kilogram of 1 kilogram mass upward against gravity 1 meter. So we'd have to do that 1,700 times to complete the phase change to take 5 grams of water from solid to liquid. That's wow, that's a lot. So you can trust that you'll be provided these values if needed. Now, what if we had the 5 grams and they were starting in the liquid state, and we wanted to find out, well, how much energy would we have to remove to fully freeze it? We'd make that negative, and then that would be negative. So however much energy we have to invest, it would be the opposite, because it's the amount of energy that has to be removed to perform the opposite phase change. What is endothermic in one direction will be exothermic in the other direction. All right. So I think we would know how we would apply these values. So the question is, are we melting or freezing? Are we vaporizing or are we condensing? But what if we have something at a temperature that's not during a phase change? Let's say you grab, 5 grams of water, probably an ice cube, out of the freezer. And what if it is at that -5 degrees Celsius? So what if we wanted to take our 5 grams, and they're not starting at the melting point? So what if we have 5 grams of water and it begins at -5 degrees Celsius, and we want to take it, let's say, to room temperature, 25 degrees Celsius. What is the energy that we would need to invest to accomplish that? Well, let's see where we're starting. Okay, we're starting, I'm going to put that in blue, starting here. Okay, if we trace our warming curve, I want to end up at 25, probably there. Now, to accomplish that, what I will need to do is first get up to the melting point, then invest the energy to melt it. Then once it's fully melted, I need to increase its temperature to get me to 25. So I'm probably going to have to break this into 1, 2, 3 steps. Well, we already went over what we would need to do to accomplish the phase change. We just did that. Now I need to get these signs back. Right? So this would be the melting. But how do I get us from the -5 to the melting point? We talked about heat before. And remember, heat we can symbolize with a lowercase q. Do we remember what we ever did with that? Remember this equation. Okay. During a phase change, that's latent heat. We can't use this equation to find heat whenever there's no change in temperature. There's no change in temperature. This is 0. It seems like there's no heat. But no, that's not true during a phase change. During a phase change, we need to use molar heats of fusion and molar heats of vaporization. Okay. But during a temperature change, we can use this tried and true MC delta T. So if we remember, Q is heat, M is mass, C is specific heat. And specific heat, the amount of energy that must be invested to raise 1 gram of substance 1 degree Celsius. So if we remember, specific heat has the units of joule per gram degree Celsius. And if we remember, not expecting us to remember, the specific heat of water in the liquid state is 4.184 joule per gram degree Celsius. So, that's probably going to help us here. So whenever we are undergoing a phase change, this will not help us. But if we're anywhere where temperature is changing, Q equals MC delta T will. So if I want to show on the graph, whatever I've marked with red, that's where we would apply MC delta T to do the calculation, where we'd apply the molar heat of fusion, put a negative sign on it if we're freezing, molar heat of vaporization, put a negative sign on it if we're condensing. Okay, so let's dig in. All right, so we already figured out melting. All right, but we need to get from -5 to the melting point. That's our first step. 2, which we know is 0 for water. All right, we are undergoing a change of temperature. So Q equals mc delta T. And we have our mass of our water. But wait, at -5, water is in the solid state. That 4.184 is when it's in the liquid state. So ladies and gentlemen, here are all the given constants that we would need to interpret the warming or cooling curve for water. So trust that you'll be given these. And just like the molar heat of vaporization and the molar heat of vaporization are different values, so are the specific heat values for water. Here, I'm just going to end this so I can keep with my calculations. So it's in the solid state. Water is solid here. So 5 grams of solid water, we need the specific heat of water in the solid state, 2.06 joule per gram degrees Celsius. Remember, delta T is final minus initial. I want to end up at 0. End up at 0 starting at the -5. So this will be 0 degrees Celsius minus -5 degrees Celsius. Okay, be careful of sig figs. So I want to do order of operations this first, and whenever we subtract, we know we are bound by the least precise decimal place. So this will end up being 5 degrees Celsius times the 2.06. This has the opportunity to limit our sig figs, but now this, when we're multiplying, limits us to 2, and there's 2 as well. Let me find what, and so 51.5, I'll have an opportunity to employ even odd rule. Now grams cancel out, degrees Celsius canceled out. This is going to be joules. Only 2 sig figs, a 5 with nothing else after it. I look to the number before it. It is odd. We would round odd to be even. If it was even, we'd keep it as is. So 52 joules, and it makes sense that it's positive because we are endothermic in that direction. Okay, then step 2 would be our phase change. And remember, we just had done that work before. So this is step 2, taking our 5 grams from solid to liquid. So we would just employ the enthalpy of fusion, or the heat of fusion, and that's also positive. Now if we notice, our step 1 is positive, 52 joules, but it's in joules. Now, if the problem asks us to find the heat in joules, we need to cooperate and give it in joules. But if it would ask for kilojoules, we have to give it in kilojoules. Otherwise, you can choose. Would you rather have it in joules or kilojoules? But they have to be the same if we need to add them. Okay, then step 3. So step 1, that was getting us from -5 to 0. That was Q equals mc delta T. Step 2 was our phase change. Okay, so let me just circle these values for us. And then step 3 will take us from 0 to 25, but we're all liquid. So Q equals mc delta T. All right, still have our 5 grams of water, but now it's all liquid. So we need the specific heat of liquid water, and 4.184 joule per gram degrees Celsius. We are ending at 25, beginning at 0. So order of operations, subtracting, this will give us 25 degrees Celsius. That'll cancel, so we're limited to sig figs of the 5 grams. All right, and we would round this to 520, and it will be joules and positive. Okay, so now how much energy? Well, it is going to be the heat from getting us from -5 degrees Celsius to 0. That's our step 1, plus the heat of the phase change, and that used the heat of fusion, plus the heat taking us from liquid at 0 up to 25. Okay, so adding those. All right, this is 52 joules plus 1700 joules plus 52 or 520 joules. Okay, sig figs again. When we're adding these, it's our least precise decimal place. So if I would lay these out vertically, 52, least precise to the 1 place. 1700, this is least precise to the 100 place. And then 520, least precise to the 10. So 2, 7, 2, 2. I'm allowed to report to the 100. So this would be 2300 joules positive to take us from -5 to 25 degrees Celsius if we had 5 grams of water. The next set of videos that are shown to you, ladies and gentlemen, walk through a couple more calculations. You just have to be really careful. Are you employing the correct specific heat? Are you allowed to apply MC delta T? Does your step actually involve a change of temperature? Do you have the correct sign? Do you have the correct units? Have you converted to grams to moles if needed? And so on. So give some more problems a try. Best of luck. That's an introduction to warming curves.